average rate of change. Remember, calculus is the study of change. We're interested in learning about patterns regarding how functions change to see if we can use that to predict what may happen later on with that function. There's a lot of value in learning about the various ways that functions change. In mathematics, when we don't know how to do something, we often start with what we do know how to do and use that to adapt to figure out what we don't know how to do. So quickly, we're going to review something that we already know about how functions change. What we know at this point is how to measure the change of a linear function. So if we have a line, the way that we talk about how it changes is with a term called slope. So hopefully you remember hearing about the slope of a line. So the slope of a line tells us how much the dependent variable changes for every one unit that the independent variable changes. The slope of a line has a lot of ways to denote that that's what we're looking for. Oftentimes, you'll see slope of a line called m. M represents the slope. You may also have seen it as delta y over delta x, the change in y over change in x. Similarly, you may have seen something like y1 minus y2 divided by x1 minus x2. There's a lot of different ways There are a lot of ways that you may have seen slope represented, but all of them give us the same measure. Again, it tells us how much the dependent variable changes. So how much do we need to change in the y direction for every one unit that we change in the independent direction or the x direction? That's what the slope of the line tells us. So what we want to do is we want to take that idea and see if we can use it to talk about how curved functions change. So consider the following example. What if we want to talk about the change of a curved function? So we have a generic function here, f of x, and we want to find out a little bit about how much it changes between x equals 1 and x equals 3. So you can see that it's a curved line. If we could cut it out and straighten it out, we might have some ideas about that length, which is something we do in geometry. But we want to look at this in terms of the way it's shaped now with that curved bend. So what we can do is we can find out how much this function changes on average by using the slope of the line that connects the two x values that we're interested in. So you can see that represented with the red line over here on our function. So if we can find the slope of that line, it'll tell us how much the function changed from the point at x equals 1 to the point at x equals 3 on average. So what we're going to do is we're going to use what we know about the slope of the line to find the slope of this line. So again, we're going to do the change in y over change in x for x equals 1 to x equals 3. So remember, we're doing change in y over change in x. Now, as long as we're consistent with the order that we pick our x's, it doesn't actually matter if we do the 1 first or the 3 first, as long as when we put in the representative y value, it's in the same order that we choose our x's. I also want to remind you that one of the ways that we can represent the y value is to talk about f of the x value. So in this case, the way that I'm going to write the change in y over change in x is using functional notation. So I'm going to notate this as f of 3 minus f of 1 divided by 3 minus 1. So f of 3 represents the y value when x equals 3. So f of 3 here, I'm going to approximate. So that means that I'm going to estimate what the y value is because I don't have a clear answer. It doesn't look like it's at an exact integer, so I have to make a good educated guess about where that value is. So looking at this y value for f of 3, I'm going to approximate that that is approximately 1.3. Now, you may approximate it a little bit different. You may have said 1.25. You may have said 1.2, Anything in that range is okay for an approximation. We want to get pretty close to what it is, but there's a little bit of room for error. So that's my f of 3 value, the y value that's connected to the 3. From that, I'm going to approximate f of 1. So that means I'm going to go up to where the 1 is, and again, I'm going to try to approximate what that y value is. So my best guess here, I'm going to call that 2.8. Again, you may approximate slightly different, but it should be relatively close to 2.8. So that's the change in y values, and then I'm going to divide that by the change in x, which was 3 minus 1. So again, order isn't necessarily important as long as you are consistent. I could have done f of 1 minus f of 3 divided by 1 minus 3, and I would end up with the same answer, but I have to be consistent with my x's and y's. So when I crunch this number in my calculator, I put that all in, and I get approximately negative 0.75. So negative 0.75 is the approximate slope of this line, which tells me that on average, my function changes by negative 0.75 in the y direction for every 1 unit that I move in the x direction. Now you can see that that's not true in every single place between 1 and 3. For instance, from 1 to 1.5, that function's increasing. So if I were to find the slope between 1 and 1.5, the slope would surely be positive. So it's important that we remember that when we do an average rate of change, it's talking about what's happening between the 2 points we picked, and not necessarily at every sub-interval between those points. However, it gives us a good idea about what's happening in terms of change of this function between 1 and 3 on average. We can calculate how much a function changes on average over an interval by computing the change in the dependent variable over the change in the independent variable by finding the slope of that line. So if we want to come up with a general formula to talk about the average rate of change, we need a way to represent the slope between any 2 points. We're going to use the points A and B here in our formula to talk about any 2 points that we're interested in looking between. So our formula here for average rate of change is going to be f of b minus f of a over b minus a. So again, when you're looking between 2 points, it doesn't actually matter how you pick your a and your b as long as you're consistent. So when you have an x value of a, the corresponding y value is f of a. And when you have an x value of b, the corresponding y value is f of b. So we're going to use this formula rather extensively throughout this course. The average rate of change is really important. And when you see the word average, that's a key indicator that we are going to be using this formula. So let's take a look at some examples of computing average rates of change. So let's start with the graphical representation of average rate of change. This is the same graph that I used in the previous example, and the red line represents the slope that we approximated in the first problem. When we looked between 1 and 3, we found the slope to be approximately negative 0.75. Now, if we're interested in looking between other points, we can apply the same formula. So let's look at this blue line. This blue line is interested in what's happening between x equals 0.5 and x equals 4.5. You can see those endpoints on the graph. And if you look at the corresponding x values, that's the interval where we're interested in. So if we're looking for the average rate of change, we need to do f of b minus f of a over b minus a. Because order only matters when connecting to the y value, I always use b for bigger. So my b value is always the bigger of the two x values. So I'm going to pick my b to be 4.5. So my formula is going to be f of 4.5 minus f of 0.5 divided by 4.5 minus 0.5. So again, I'm going to have to do a little approximating. I need to take each x value and approximate where the y value is. And again, it doesn't have to be perfect, but we should be relatively close to the same estimates. So at 4.5, if I go down and I look at the corresponding x value, that seems pretty close to -1. So I'm going to say that my y value is -1 minus. Now I go to 0.5 and I go up to the corresponding x value. That looks really close to 2. So I'm going to say that my y value is 2. And that's divided by 4.5 minus 0.5, or 4. So remember with negative numbers to be extra careful. -1 minus 2 is going to give me -3 over 4, or approximately -0.75. So the slope of this blue line is approximately -0.75. That's interesting because that's what we approximated our red line to be earlier. However, I noticed that when I look at the slope of these two lines, that I would expect them to be the same because these lines look relatively parallel, and parallel lines have the same slope. So this makes sense that my approximations would be really close for these two lines. So now let's consider what's happening between 0 and 2. The green line has an upward slope, so I'm expecting something different than the other two approximations. Additionally, I'm expecting the slope to be positive since my line goes in the upward direction. So again, I'm considering what's happening between x equals 0 and x equals 2. So that means my formula is going to look like f of 2 minus f of 0 divided by 2 minus 0. So f of 2 is another approximation. So I go to 2 and I go up to where it hits the function, and I need to approximate the corresponding y value. For me, I'm going to say that this is approximately 2.8 is my best guess. Hopefully, your approximation is something similar. My f of 0, if I look at where 0 hits, is really close to 1. So my y value there is going to be 1 divided by 2 minus 0, which is 2. So again, I'm going to crunch this number in my calculator, and when I put it all in, I get an approximation of 0.9. So again, I was expecting the slope to be positive, and it was, so that's good news. So here, the slope of this green line is approximately 0.9. So again, that tells me that on average, my function changes by 0.9 units in the y direction for every 1 unit in the x direction between 0 and 2, because those are the 2 points that I was considering here. Turns out that this line that we're using to approximate the average rate of change has a special name. When using a line to approximate the average rate of change between 2 points of a nonlinear function, that line is called the secant line. And the average rate of change is the slope of the secant line. So the slope of the secant line tells us the average rate of change, and the secant line connects 2 points of a nonlinear function. Note, the average rate of change of a linear function, or of a line, is just the slope of that line. And if it turns out that when you're computing average rates of change over a function, if they're all the same, then that function is linear, because the slope would be the same everywhere. Let's look at a few examples of how we can compute average rates of change in other ways that are not on graphs. So first, let's look at an example of a formula here that's y equals f of x equals x squared plus 3x minus 1. And let's try to find the average rate of change between x equals 1 and x equals 4. Since x equals 1 and x equals 4 is the interval where we want to calculate our average rate of change, that's our a and our b. I'm going to use 1 as my a and 4 as my b. Again, it doesn't actually matter how I pick my a and b as long as I'm consistent in the formula. So the formula again was f of b minus f of a over b minus a. By substituting in the values I have for this particular problem, that means I'm looking for f of 4 minus f of 1 divided by 4 minus 1. Now, since I don't have a graph here, I'm going to be finding my y values by plugging my x values into my function. So here, when I plug in a 4, I'm going to have 4 squared plus 3 times 4 minus 1. So when I crunch that number, I'm going to get 27. So that's my y value up in the top. I also need to calculate f of 1. So again, I take 1 and I plug it back into my original function here. And then I crunch all the numbers. And so here, f of 1 is going to give me 3. So I go back and I plug that in for the y value, divided by. Now on the bottom, I have a 4 minus 1, which is 3. So I have 27 minus 3 divided by 3. And when I crunch that number, I get 8. So this function, on average, changes by 8 units, which is positive in the upward y direction, for every 1 unit that the function changes in the independent or x direction between x equals 1 and x equals 4. So the average rate of change here is 8, because again, we're talking about how much that function changes on average. We can also look at the average rate of change by using a table. So suppose the table below is continuous and gives the data of a population P in thousands measured in years T since 1970. One of the things that we need to address here is the fact that this function is a continuous function and the data reported on the table just gives us a snapshot. We talked before about what it means to be continuous versus discrete, and while tables are normally discrete, we can talk about information from a continuous function. So what that means here is that even though we don't know what's happening between the various t values, we know that they are connected in a continuous way. So if we want to talk about some of the various things on the table related to average rates of change, we want to go ahead and calculate that using the same formula. So there's 3 questions here regarding this table. The first is, what was the population in 1970? This particular question is important because we have to situate ourselves with what T represents. So T is in years since 1970. Then if we're talking about the population in 1970, that would correspond to T equals 0. So if we go to the data at T equals 0, we know that the population at that time is 60,000, because remember that the population is given in thousands. So whatever this population is representing, in 1970, there were 60,000 in this population. If we want to consider the average rate of change of this population, we need to look between 2 given points. So in question 2, we're asking what was the average rate of change between 1970 and 2000. So we need to figure out what the corresponding t values would be so we can use our table. So remember, t is in years since 1970, which means that 1970 corresponds to t equals 0. And 2000 is going to correspond to t equals 30, because it would have been 30 years since 1970. So that means when we plug this into our formula, that our a and our b are going to be 0 and 30. Up until this point, the way we've used our formula is with f of b minus f of a over b minus a, because we were using the generic f of x. Here our function is p of t, so we can adapt our formula just a little bit. We'll do p of 30 minus p of 0 over 30 minus 0. So instead of using f's, we can use p, since that's how this particular problem was defined. So we're going to take these and we're going to find the dependent value at 30. So the independent value of 30 gives us a dependent value of 85. The independent value of 0 gives us a dependent or y value of 60, all divided by 30 minus 0, which is 30. So now, if we crunch that number, we are going to approximate this. This is going to be 0.833 thousand. Now, why did I say this was an approximation? Because when you crunch this number, you get 0.833 repeating, and therefore, you need to round it off somewhere. So it becomes a slight approximation. So we get 0.833, and we have to remember that population is in thousands. So we have to add the word thousand to remember what our units are in this particular problem. So that means that this population changed by 0.833 thousand per year from 1970 to 2000 on average. Similarly, if we wanted to find the average rate of change between 1980 and 2010, we first need to figure out what our corresponding t values are. So 1980 is going to correspond to t equals 10, because that's 10 years after 1970. And t equals 2010 is going to give us t equals 40. So again, we can use the notation with the p here because we don't have an f of x, we have a p of t. So when we apply our formula here, we're going to have p of 40 minus p of 10 divided by 40 minus 10. So p of 40, we go to our table, we get the corresponding y value, which is 100. P of 10, we get the corresponding y value, which is 65, divided by 40 minus 10. 40 minus 10 is 30. So again, we're going to crunch that number, and we're going to get 1.167 approximately, and that's in thousands. So 1.167 thousand per year is what our population is changing on average between 1980 and 2010. So we can apply the formula to tables just like we could for graphs. Let's take one more crack at a graph to finish this up, and then we'll talk about some other real-world applications that this has. Consider the graph below. If we want to find the average rate of change from x equals 0 to x equals 4, we want to find the slope of the line that connects the function at 0 and x equals 4. I've signified this with the blue line. Remember, the name of that line is the secant line, and we're trying to find the slope of that secant line. So again, we're going to apply our formula here. We're going to do f of 4 minus f of 0 divided by 4 minus 0. And we're going to get those values from our graph. So f of 4, if you go up to where x equals 4 hits the graph, we come over and we find a corresponding y value of approximately 2. Then if we go to f equals 0, we can see it doesn't touch exactly at the origin, so it's a little bit above 0. So for my approximation, I'm going to call that 0.1. And then on the bottom, we're dividing by 4. Crunching that number, 2 minus 0.1 divided by 4 is going to give us 0.475. What that tells me that on average, this function is going to change by 0.475 in the dependent direction for every 1 unit I change in the independent direction on average. One of the applications that we will carry throughout the semester involves the relationship between distance and velocity. So we're going to take a minute to define these two terms so we can do our first application, which will be the average rate of change, to see what it tells us about these things. So distance is the measured length between two positions. So you may have one object that goes from one point to another point, and distance is the length between those 2 points. This can be measured in feet, kilometers, miles. It really depends on what you're looking at. In mathematics and physics, position is often notated using capital S of t. So if you see that within a problem, you're probably talking about position. Although we don't always use it, sometimes we still use f of x. That is a typical way to indicate that we're talking about distance is by using the s of t. Velocity is the rate at which our position is changing. So how quickly did we get from the first point to the second point is what our velocity tells us. In mathematics and physics, velocity is often notated using v of t. So you can imagine that if we look at the average rate of change of distance, that's actually going to tell us the average velocity, or how quickly it's changing on average between the 2 points that we're interested in. So in the example below, we'll explore this relationship a little bit, but we'll see these terms carry out throughout the semester, so we'll circle back to them. So example 4. Suppose the position of an object falling off of a building can be found using the formula s of t equals 2,704 minus 16t squared, where position, s of t, is measured in feet, and time t is measured in seconds. First, find the time when this object hits the ground, then find the average velocity of this object from t equals 3 to t equals 6. So there's some interesting things happening in this problem. The first thing we want to try to calculate is when this object hits the ground. So when the object hits the ground, the position of the object will be 0 because it will no longer have anywhere to go. So if position equals 0, that means we can take our function and set it equal to 0 to find the time when this object hits the ground. By setting this equal to 0, this turns this first part into an algebra problem. So we can bring the 16t squared over to the left, and we get 16t squared equals 2704. We can divide both sides by 16. On the left it'll cancel, and on the right we'll be left with 169. If we take the square root of both sides, we get t equals plus or minus 13. Remembering that t represents time measured in seconds, time equals negative 13 doesn't make sense. So we know here that we must be looking for the positive root here. So t equals 13. So after 13 seconds, the position will be 0, meaning that this object has hit the ground. So t equals 13, and underneath it, I'm just going to notate that that is in seconds. So that's the answer to our first question. Find when this object hits the ground. Next, we want to find the average velocity of the object from time equals 3 to time equals 6. So again, we have 2 points, and we're interested in how the function changes between them. Remember, the velocity talks about how quickly the position changes. So the average velocity is the average rate of change of the position function. So here, I'm going to use s of 6 minus s of 3 divided by 6 minus 3. So that's the average rate of change of the position function. And again, I'm using s here because that's what was given to me in the problem. So if I want to find s of 6, I need to take 6 and I need to plug it into my s function. Being very careful with the computation, I'll do that in my calculator, and I get 2,128 minus, and then I'm going to compute s of 3. So again, I'm going to plug that into my calculator very carefully, and I get 2,380, and that's all going to be divided by 3. When I crunch that number one final time, I get negative 84. So now is a good time to talk about units, because in this problem, for the first time, we have some units that we can talk about this rate. So the units on the top part of my function have to do with the position. Remember, I did s of 6 minus s of 3. S of t was measured in feet. So the top part of my number was in feet, but the bottom part of my number, 6 minus 3, had to do with the time. And remember, time is measured in seconds. So my bottom number was in seconds. So that means that when I crunch these numbers together, I get negative 84 feet per second. So it's the units of the top over the units of the bottom. The negative tells me that my object is falling in the downward direction. I could be talking about tossing a ball upward, and I may have a positive velocity, but here it's going to be negative because it's falling. So here, the average velocity of this object is negative 84 feet per second. So that means it's going to fall by 84 feet for every 1 second that goes by, on average, between time equals 3 and time equals 6. The next concept we want to talk about is something called concavity. We're building our vocabulary to describe what happens on a graph. So concavity is going to describe how a function bends. So far, we've only looked at increasing and decreasing as terms used to describe a graph, so this will help us build a better vocabulary to better describe what a function is doing. So the first concavity that we're going to look at is something called concave up. So a function is concave up on an interval if it bends in the upward direction from left to right. So imagine concave up looks like a cup. Additionally, if you look at the average rate of change between points as you move from left to right, the average rates of change are going to be increasing. So the slope is going to be going and getting steeper and steeper in the positive direction or less and less steep in the negative direction. So here's an example below of a function that's concave up. So you can see that it bends upwards, it looks like a cup. And if you calculate the average rate of change from -3 to -2, the orange line, you see that that slope is -5. The average rate of change from -2 to -1 is -3, that's the blue line. From -1 to 0, we have a black line. The slope of that line is -1. And you can see that the slope from 1 to 2 is going to be +3. So if you look at what those average rates of change are doing, we have -5, -3, -1, +3. Those slopes are increasing. So that tells me that I'm bending in the upward direction. So even though I can see that visually now, that's helpful to know in case we're trying to describe concavity of something when we don't have the graph. So this is a way that we can check to see which way the graph bends by looking at these average rates of change and considering what they're doing. So the counterpart to that is if a function is concave down. A function is concave down on an interval if it bends in the downward direction from left to right. Additionally, if you look at average rates of change between points moving from left to right, average rates of change of a concave down function are going to be decreasing. So consider the picture below. So this particular function is concave down. And if you look at the average rates of change represented by different colors, slopes of these secant lines, we have 5, 3, 1, -1. So these slopes are decreasing as we move from left to right. So that helps me determine that the bend was downward and that this particular function is concave down. While visually, it's relatively easy to determine if a function is concave up or concave down by looking at it, we want to use those conditions that relate to average rates of change when we're looking at functions and we don't have the complete picture. So for example 5, we're going to do just that. Assume that the function represented below is continuous. Determine where the following function is likely to be concave up and concave down. So here, we're going to have to rely on the average rates of change to help us determine where we think a good place for this to be concave up and concave down will be. So what we want to do is we want to go ahead and we want to find the average rates of change between the points for the entire table. So remember, we can apply f of b minus f of a over b minus a between any 2 points. So we're going to go ahead and do this multiple times. Consider the first interval. So the x values here are 0 to 2. So when we're calculating the average rate of change between 0 of 2, we'll do f of 2 minus f of 0 over 2 minus 0. F of 2 asks you to find the independent value of 2 and then find the corresponding dependent value, which here is going to be 12. So we have 12 minus And again, we'll go to f of 0, which means we have an independent value of 0, and we want to find the dependent value, which is 10, divided by 2. 12 minus 10 is going to be 2. 2 divided by 2 is 1. So we get an average rate of change of 1 between x equals 0 and x equals 2. Since we're doing change in y over change in x, we can do this a little more quickly as we move down the table. So when we consider what's happening between 2 and 4, we can look at the change in y as 16 minus 12 divided by 4 minus 2. 16 minus 12 is going to give us 4. 4 divided by 2 is going to give me 2. If I do the change in y over change in x between 4 and 6, I will do 22 minus 16 divided by 6 minus 4. That's going to give me a value of 3. If I do the average rate of change between 6 and 8, I will be doing the change in y, which is 30 minus 22, which gives me 8, divided by 8 minus 6, which is 2. 8 divided by 2 is going to give me 4. From 8 to 10, the change in y over change in x will be 35 minus 30, which is 5, divided by 8 minus 10. 5 divided by 2 is 2.5. The average rate of change between 10 and 12 will give me 1.5. And finally, the average rate of change between 12 and 14 will give me 0.5. So what I need to consider, again, is what happens as I move from left to right. If my values are increasing, that means that my function is bending upward and I'm concave up. If my values are decreasing, that means that my function is concave down and bending downward. Notice here that I'm going to be increasing from 0 to approximately here. And we'll talk about what that point means in a second. And then we're going to be decreasing 4, 2.5, 1.5, 5 for this interval here. So we need to figure out a way to represent where we're increasing and where we're decreasing. We don't know exactly where this change happens, right? It could be at 6, 6.1, 6.2, 6.3. So we have to make a pretty good educated guess. So right in the midpoint of 6 and 8 is 7. So that's a pretty good place to cut it off. So we're going to say that we believe that we are concave up from x equals 0 to x equals 7, because again, that's where my average rates of change are increasing. We're going to say that we're concave down from x equals 7 to x equals 14, because that's where my average rates of change are decreasing. And again, the 7 is a little bit arbitrary. I could have said x equals 0 to x equals 6, and then x equals 8 to x equals 14. 7 was the compromise in between, but with the understanding that somewhere between 6 and 8 is where we're going to change from concave up to concave down. Finally, we want to put this concavity idea together with the increasing, decreasing definitions we learned in the last section, because these are the ways that we're going to be using to describe graphs throughout this course. So here, using the graph below, we want to determine the intervals where this function is increasing, decreasing, concave up, and concave down. So there's 4 different things we're assessing: increasing, decreasing, concave up, concave down. So let's look at each one individually. So first, let's consider where this function's increasing. So remember, we're going to be increasing if as the x values increase, the y values increase, and we'll be moving in an upward direction. So here, it looks like the first interval where we're increasing is going to be from x equals 0 to x equals 0.5. So we'll use our interval notation to indicate that. We are not going to include the endpoints because, again, when we turn around from increasing to decreasing, at that particular point, you're considered constant. I also want to point out that we're increasing on another place over here on the right. So 1.5 to 2, we are again moving in the upward direction. So we're also going to include that on our increasing. So for x between 1.5 and 2, we are also increasing. So now we can say that we are decreasing from x equals 0.5 until x equals 1.5, because again, as we move from left to right, or our x values are increasing, our y values are decreasing. They're moving in the downward direction as we go from left to right. So now let's talk about the concavity. First, let's look and see if we can figure out where this graph is concave up. Remember, concave up bends in the upward direction. It tends to look like a cup. So here, between 1 and 2, this particular function bends in the upward direction. So that means that for x between 1 and 2, our function is concave up. If we're looking for where it's concave down looks like a frown, right? It's bending downward like a hill. We see that that happens from 0 to 1. So between x equals 0 and x equals 1, our function bends in the downward direction. So when we evaluate graphs, we now have two different categories to put our graphs or functions into. We can talk about increasing, decreasing as the first descriptor category, and concave up and concave down for the second descriptor category. And it's important to remember that when we talk about concavity, that we have this relation to the average rate of change. The average rate of change is going to increase as you move from left to right if your function is concave up, and it's going to decrease as you move from left to right if your function is concave down.